Hello everyone. Thank you for attending the BAS Electrochemical Webinar 2021 June. I'm Miho from International Sales Team and I will be the moderator. Before we start, as usual, we will ask you to don't be worried to record and enjoy the webinar. We are recording and we will send the direction to you as soon as it is ready. In this way, you will be able to review the full webinar. Also, if you have any question, please feel free to contact us. Well, let's start today's webinar. Today, it will be the second lecture introduced by Professor Noriyuki Watanabe, a former assistant professor of the Faculty of Engineering at the University of Tokyo and BAS Technical Advisor. The theme is Basics of Electrochemistry, Fundamental Electrochemistry Part 1.
Today I will give you the lecture titled like this, Fundamental of Electrochemistry, and it's part 1. There is a lot of things about electrochemistry. That is, what is it, why it is so important, how it is learned. There is no royal road. You have to make hard learning step by step. First of all, I mention about redox potential. Redox potential is important subject in electrochemistry. This subject is categorized in thermodynamics. Another important term is rate of electron transfer. This is classified as kinetics. Those two are main fundamentals in physical chemistry. Thermodynamics is rather static matter, while the kinetics is a dynamic parameter. Physical chemistry is a major lecture item in university, but about electrochemistry is rather very few. We don't have time to hear about electrochemistry in university, but electrochemistry is a very important matter. Today's lecture is about redox potential. I will give you about the rate of electron transfer in a future day. Let's say as soon as possible. Recommended concept about towards the direction of energy scale. Downward direction is more stable in gravitation for material having weight. Now we consider about electron. For electron having a negative charge, so the direction to downward is more stable for electron. Schematically shown below. This is energy level of electron. Stabilized direction is downward, while unstabilized, excited, in this case, direction is upward. Electron is stabilized toward downward direction. Redox electron potential is downward is stabilized direction. Now I mention about the formation of Hopolmo levels for atomic orbital. This atom and atom's orbital is like this. In the case of two atoms and each other departed like this, almost same atomic level, energy level. Now these two atoms take close formation of bond. Like this, energy level is split like this to energy level. This stabilized level is called as HOMO, highest occupied molecular orbital, and another unoccupied level is LUMO. Lowest unoccupied molecular orbital is abbreviation. When we discuss the chemical reaction or energy level, we say molecular orbital theory. MO is abbreviated. Energy level and the distribution of electron in a molecule. Two atoms via two electron formation of a molecule. Two atoms, this and via two electrons, the formation of molecule is made. Two atoms formation of a molecular orbital. The two atoms make bonding by closing, and each electron is enter into lower level, lower energy level, making pair. This lower level is bonding level, and anti-bonding orbital is occupied. Making bonding energy level split to high, lower and higher molecular orbital. This is a schematic diagram of molecular orbital. Electron enter the lower level step by step to upper energy level, making a pair of electron. Two electrons enter one level, upward and downward direction. Electron enter into energy level from lowest level to upper level by 2 each in same level, directing reverse direction each other. Electron is taken out from HOMO by oxidation. Highest occupied molecular orbital electron in HOMO is taken away by oxidation. Electron enter into LUMO by reduction. This slide shows the scheme of electrode potential and redox reaction. This is electrode, and this solution contacting electrode. Redox moiety is dissolved in solution. Electrode, this Fermi level of electrode. Now applying potential to electrode, this positive potential direction and this negative direction. Now potential of electrode is applied to positive and Fermi level reached to HOMO level of solution species. Then the electron is taken away by electrode. This corresponds to oxidation. Now this in the case of reduction, electrode is Fermi level of electrode is applied minus potential, so Fermi level up move to upward, and Fermi level reached to LUMO level of molecular species. Then from this Fermi level, electron move to LUMO level of solute. This corresponds to reduction. This schematic is relation between electron and species in solute. I am going to tell you mainly about organometallic compound, but essential of the story is applicable to other general molecule. So d orbital splitting of octahedral coordination compound of transition metal, like this. In this case, for example, ferrous ion. Ferrous ion Fe2 plus is typically applied in this case. Ferrous ion. This HOMO level of ferrous ion, and this splitting by interaction of ligand. back donation from central metal to ligand is important consideration. This central metal and this ligand. Ligand coordinate to central metal donate electron and back donation from central metal to ligand like this. The outer orbital electron is move to ligand or from ligand. The bonding is formed like this. Carbonyl or cyanate, alkyl cyanate. These are typically and with strong tendency of receiving back donation. This back donation is work for bonding. This is another scheme. This metal d sigma orbital, and this carbonyl lone pair donate to metal center. While the back donation is occurring this bonding from metal to unoccupied carbon bonding. This back donation. This bonding works for bond formation. Being pi acidic in nature, carbonyl is a strong field ligand that achieves greater d orbital splitting through the metal to ligand pi back donation. Metal carbonyl bonding interaction thus comprise of CO to metal sigma donation and metal to CO pi back donation. This two mechanism concert bond formation. Both the spectroscopic measurements and the theoretical studies suggest that the extent of the metal to CO pi back donation is almost equal to or even greater than the extent of the CO to metal sigma donation in metal carbonic complex. This indicates the fact that low valent transition metal center tend to form metal carbonic complex. Like first transition element, vanadium, chrome, mangan, iron, nickel, cobalt, nickel. That's a typical transition metal element. Carbonyl is a very important player in organometallic chemistry. So often I mention about carbonyl compound. This slide shows a schematic drawing of donation sigma and back donation pi bonding. These two bonding concerted strong bonding in organometallic complex. This metal center and this carbonyl. The carbonyl lone pair donate to metal unoccupied orbital. This is a sigma bond, and this pi bonding. This unoccupied orbital, pi star orbital, is taking d pi electron. This work as a strong bonding between metal and carbonyl. This schematic drawing of sigma bond and pi bonding. If a molecular orbital back donated is anti-bonding, the bonding is weakened. Typical example is carbonyl. The extent of back bonding for carbonyl is able to be estimated from the decrease of stretching frequency in infrared spectroscopy. Typical stretching frequency is around 1,800 Kaiser. This is a typical frequency carbonyl compound. About the infrared stretching frequency of carbonyl ligand. Coordinated or free carbonyl, this like this, 2,143. This is a free free carbonyl. However, by molecular bonding, frequency is decreased. Frequency decreased to 1,080 Kaiser from 20,000 to 2,000 Kaiser. W bridging. This Kaiser decreased to more 1,700 Kaiser. And triple bridging or triple bridging further decrease in stretching frequency. So infrared stretching frequency of carbonyl decreased with increasing coordination number. So we can estimate the degree of coordination. We can estimate how extent coordinated. relation between electron density of redox center and redox potential shift. This is also very important subject. Electron density of redox center. This, for example, ferrocene. Increase of electron density, negative shift of redox potential. Decrease of electron density, this time positive shift of potential. What is the factor causing increase or decrease of electron density? This is we have to consider the and very we need to those background to estimate the resultant phenomenon. Various factor led to electron density increase or decrease. One of them is influenced by substitutional groups. For example, in ferrocene. Ferrocene is like this central ferrous iron is sandwiched by cyclopentagenyl ring. This is cyclopentagenyl abbreviation. This carbon, 5 carbon and hydrogen atom bonded. So C5 and H5 is a molecular formula. These are important and very typical molecule for discussing the organic electrochemistry of organic metal. Ferrocene is a molecule which is sandwiched by two cyclopentagenyl groups. This is a cyclopentagenyl and ferrous iron is sandwiched by. Electron density around the central iron atom of ferrocene is affected by substitutional group of cyclopentagenyl ring. This H is substituted to another atom or alkyl group. For example, substitution of H hydrogen in Cp by methyl or other alkyl group, electron additive group. Alkyl group is an electron additive group or acetyl group. Acetyl electron withdrawal group. Alkyl additive. This acetyl group is withdrawal group. So acetyl group electron withdrawal affect electron density in different way and extent. Thus, redox potential for ferrocene is increase or decrease direction. Today's summary. Electrochemistry relates to two fundamental fields of science, that is thermodynamics and kinetics. Redox potential and electron transfer rate. This thermodynamic parameter. The electron transfer rate is kinetic. This static and this dynamic. To discuss these two subjects is electrochemistry. Today's lecture is that's all.
Thank you, Professor Watanabe. I hope you enjoyed the lecture. If you have any question regarding to the lecture or other topic, please always feel free to contact us. The email is here. Also, if you, we will be sending the direction to watch and review the full webinar, together with the direction to answer the survey, which will be used for the improvement of the future webinar. In addition, in the technical note of ALS website, you can find collection material focusing on basic contents for beginners who are starting electrochemistry, written by Professor Noriyuki Watanabe. And the movie of variety of the topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar, Fundamental Electrochemistry Part 2, we are working out to have it for July. For today, thank you again and stay safe and healthy.